hear the word mathematics, what words come to mind? Would it be numbers, equations, operations like addition or subtraction? While these words are significant to mathematics, it goes beyond what we typically think of. It provides us with answers to real-world phenomena and can explain why things in our world function the way that they do. Some mathematicians study spaces, surfaces, and how shapes behave when they curve, stretch, or are deformed. This area of mathematics is called geometry, specifically hyperbolic geometry or the study of curved surfaces. These ideas help mathematicians understand complex shapes, connect other branches of mathematics, and even contribute to fields like physics and cosmology. In advanced geometry, mathematicians ask questions like, how do complex surfaces behave? How many ways can a surface change its shape? And can we measure and classify all these possibilities? To answer these questions, mathematicians study Riemann surfaces, moduli spaces, and dynamical systems. For a long time, these topics were studied separately and were difficult to connect. Not until this one woman made history.
So, who exactly is this woman? Let's meet Maryam Mirzakhani. She was an Iranian mathematician and one of the most influential women in modern mathematics. She is best known as the first woman and the first Iranian to receive the Fields Medal, the highest honor in mathematics. Her work changed how mathematicians understand geometric surfaces. Maryam Mirzakhani was born in Tehran, Iran in 1977. As a student, she showed exceptional talent in mathematics and became the first Iranian woman to win gold medals at the International Mathematical Olympiad in 1994 and 1995. In 1999, she graduated with a Bachelor of Science degree in mathematics from Sharif University of Technology in Tehran. She earned her PhD from Harvard University 5 years later, with her dissertation titled Simple Geodesics on Hyperbolic Surfaces and Volume of the Moduli Space of Curves. Between 2004 and 2008, she worked as a mathematics assistant professor and research fellow at the Clay Mathematics Institute of Princeton University. She then became a professor at Stanford University in 2008. Known for her quiet determination and creativity, Mirzakhani often approached mathematics through visualization and deep intuition, drawing surfaces and diagrams as part of her thinking process. Her colleagues describe her as ambitious and fearless in the face of problems others would or could not tackle. She denied herself the easy path, becoming a self-proclaimed slow mathematician. The energy and effort she spent in the longevity of her work allowed her to see the beauty of math. She continued her work despite battling cancer and, unfortunately, passed away at the age of 40.
Maryam Mirzakhani made major contributions to the field of mathematics, using the concepts of hyperbolic geometry, Riemann surfaces, Teichmüller theory, and dynamical systems. In hyperbolic geometry, Mirzakhani studied closed geodesics. These are closed curves whose length can't be shortened by deforming them.
The long-standing problems regarding the counting of these geodesics were solved with the utilization of curved hyperbolic surfaces, linking their number and their distribution to volumes of moduli spaces of Riemann surfaces. She discovered that while the total number of general geodesics grows exponentially with length, the number of simple geodesics only grows polynomially.
She was able to prove what happened to the prime number theorem for geodesics. Consequently, her works on Riemann surfaces studied how these can be classified and compared by considering all structures simultaneously, seeing how they can change or deform.
Where every Riemann surface of genus greater than 2 admits a unique hyperbolic structure, counting and measuring these geodesics under a constant negative curvature translated geometric problems into analytic and topological ones.
In the Teichmüller theory, it states how a surface can be smoothly deformed without tearing or gluing. Considering this, Mirzakhani was able to examine the space of all possible shapes a surface can take. Lastly, one of her most important achievements was discovering new formulas for the calculation of the Weil-Petersson volume in her thesis. These are volumes of moduli spaces of bordered Riemann surfaces. one of the central concepts in modern geometry. She discovered that this corresponds to a property of the modulus space.
Think of it as a pair of pants. In terms of its illustration, Mirzakhani discovered the recursive formula by proving that any complex surface can be decomposed or cut into smaller pieces that look like a pair of trousers. By understanding these pants, she could mathematically build back up to understand the most complex shapes imaginable, transforming an impossible problem into one that could be solved step by step. Using these volume formulas and her recursion, she provided a brilliant independent proof of the celebrated physicist Edward Witten's conjecture concerning how surfaces intersect looking at quantum gravity, where one through geometry and one through particle physics were actually the same. While others had proven it using complex algebra, Mirzakhani proved it through pure geometry, showing that the way surfaces intersect in higher dimensions is directly linked to the simple lengths of the geodesics that we started with. In dynamic systems, she and Eskin also co-proved the magic wand theorem. It showed that the paths of complex systems, like billiards on a polygonal table, are surprisingly regular and algebraic rather than fractal. This means that even in systems that appear chaotic, there is an underlying mathematical magic that keeps them in perfect order. She also proved that earthquake flows, which is William Thurston's way of describing how a surface geometry changes along shifting fault lines, is ergodic, meaning it eventually visits all parts of the space in a predictable way.
With that, her works related to dynamical systems studied how geometric structures evolve over time. Her works in hyperbolic geometry, Riemann surfaces, tight Miller theory, and dynamical systems explain how complex surfaces behave and change.
Maryam Mirzakhani's work was significant not just because it solved difficult problems, but because it connected areas of mathematics that were once thought to be separate. By studying how curved spaces can behave and change, she helped mathematicians better understand the deep structure of geometry itself. Her discoveries answered long-standing questions about moduli spaces, which are spaces that describe all possible shapes surfaces can exist, and opened new paths for future research in geometry and dynamical systems.
As part of her greatest achievements as a mathematician, Mirzakhani showed that geometric objects such as geodesics and hyperbolic metrics, topological data such as surface genus and curve intersections, and dynamical behavior such as flows and orbit closures are different expressions of the same underlying structure. To put it simply, counting curves is a geometric problem, understanding their distribution is a dynamical problem, and classifying surfaces is a topological problem, where all three must be studied together.
Her contributions also extended beyond pure mathematics. The ideas she developed have strong connections to theoretical physics, especially string theory, where understanding the geometry of surfaces is essential. This shows how abstract mathematical thinking can eventually help explain how our universe works on a deeper level. But perhaps her impact goes way beyond equations and theorems. As the first woman and first Iranian to receive the Fields Medal, Maryam Mirzakhani broke powerful gender and cultural barriers in mathematics. In a field long dominated by men, her success challenged stereotypes and inspired women and underrepresented groups all around the world to pursue mathematics with confidence. Mirzakhani once said that being a mathematician means trying to understand something that no one has understood before. Through her patience, creativity, and determination, she showed us that mathematics is not about speed or competition, but about curiosity and persistence. Her legacy reminds us that with passion and courage, it is possible to change an entire field and inspire the next generation to do the same.
Given all of this, there is no doubt that Maryam Mirzakhani's life and work have significantly changed our perspective on mathematics, and they show that excellence in mathematics knows no gender or nationality. With her groundbreaking contributions to the understanding of hyperbolic geometry, she truly made an impact in breaking down complex concepts that were difficult to connect and comprehend before. So, the next time we study mathematics or see a woman pursuing science, we are reminded that persistence, creativity, and passion can reshape an entire field. With her quote, "The beauty of mathematics only shows itself to more patient followers," We must let her be an inspiration to all of us, especially the youth, to stay curious and be open to discovering more ideas, to help us understand our world on a deeper level, and to find solutions to complex problems.